All right, so let's work this problem. I want to determine the slope and displacement at the midpoint of this beam. Okay, that's not an unusual problem. Typically, around the middle of the beam is where you might think the displacement would be maximum, where the slope would be near zero. But this load is slightly off-center, so the midpoint won't be the max, but it'll be close. So thinking about that, I want to find the value at the midpoint. So when we build our conjugate beam, we're going to want to find the shear and moment at the midpoint. So the first step in all these problems, if you're using conjugate beam, is to do what? Construct your shear moment diagram. So I know at A that I have, I'll assume that I have positive shear at A and positive shear at B. And of course, this is a pin and this is a roller, so I know the moments are zero. So I just need to find those two reactions. This shouldn't take too bad, just a simple point load. Before we go any farther, if I wanted to solve this with direct integration, how would I proceed? Can you write one moment equation for the whole structure? No, you'd have to write one that was valid from 0 to 9, and then a second one is from 9 to 12. And so you'd end up with 4 integration constants. You'd have to do some matching. You might end up with simultaneous equations. So it is doable. We've talked about this before, but for this particular problem, I think conjugate beam would be more appropriate. So let's go ahead and find our reaction. So I'm going to sum moments. I think I'm going to sum moments about B. No particular reason. I just will. And summing moments about B using right-hand rule, my applied 5-kip load is creating what kind of moment about B? Positive or negative? Positive moment. So the moment will be a force of 5 kips, and the distance from A to that load is 3 feet. The other force in this system is the shear force at A, and it's creating what kind of moment about B? Negative. So there's the shear at A is the force, and the distance is 12 feet. So it looks like the shear at A is going to be 1.25. And then I can sum forces in the y direction and make sure that's in equilibrium. And when I do that, I should be able to find the shear at B. So I'm going to assume up is positive, so my shear force at A is up. My positive shear force at B is down, so that would be negative. And my load, my 5-kip load, is down. That is also negative. So when I solve for the shear at B, it looks like I get negative 3.75. So it looks like I'm going to start off with a positive shear at A and transition to a negative shear at B. And that's all I need now to draw my shear force and bending moment diagram. So I'll start with a template where I'll have defined the edges of the beam. I know my shear is going to change right here as I go from the left to the right side of that applied force, so I'll add that to my template. And now we're ready to go. So I'll go ahead and define positive x-axis, positive axis for shear. All my shear units will be in kips. And what is the shear at A? Looks like it's positive 1.25, so I'll start there. 1.25. And we know the change in shear between these 2 points is what? Area under the load curve. What's the area under the load curve between those 2 points? 0. So no change. So it stays 1.25. And we also know the slope of the shear diagram is equal to the load at every point. The load at every point is 0. So that's a 0 slope, which is for us a horizontal line. So you can see that the shear is constant, and 1.25 for the first 9 feet. Yeah.
Should VB be a positive?
No, because see, I assumed it's shear, right? And positive shear is down, so since it's negative, the force is actually up. So as we go from the left side to the right side, how much does our shear change? Well, it's 5 and it's down, so that's negative. So that brings us to negative 3.75. The change in shear between any 2 points is the area in the load curve. It's 0, so there's no change. So we're going to stay at negative 3.75, which is great because that matches the shear at B. And we know the slope of the curve is equal to the value of the load. The load is 0 everywhere, so 0 slope. And there's your shear diagram. Any questions about that? Again, if you got this as just a shear and force and bending moment diagram problem, you'd be very happy, I think, on the exam. Probably not going to have that. Your happiness won't depend on this problem, though, because you won't get one this easy. Well, maybe as part of a conjugate beam problem, but... All right, so let's go ahead and do the moment. So there's positive x, there's positive moment. Our units will be in kip feet. So what is the moment at A? It's a pin, so it's 0. We also know the moment at B, at the roller. It's also 0. Now we know the change in moment between the 2 points is equal to the area in the associated part of the shear diagram. So this little section over 9 feet, it's a rectangle. That's pretty easy to calculate the area of a rectangle. It's just the base 9 feet times the height 1.5. What is that? 11.25? And we know so that's the change, and we know the slope of the shear diagram is given by the value of the shear. The shear is constant and positive, so here's a constant positive slope. And the change in moment from 9 to 12 would be the area under the portion of the shear diagram, which is 3, the base, and the height is negative 3.75. Let's hope that's 11.25. And that's negative, so that brings us back to 0. That checks. And then we know the slope of the moment diagram is given by the shear, and the shear has a value in that range that's negative and constant. So here's a negative constant slope, and there's your moment diagram. Perfect for conjugate beam because we're going to apply this now, divided by EI, as load to the conjugate beam. So you should be able to handle a triangular shape loading. So let's come over here and construct our conjugate beam. So we're going to move into this space that we've talked about where shear and moment in the conjugate beam map back to slope and displacement in the real beam. So an external pin or roller in real space maps to what in conjugate space? A pin or roller. So this beam actually, from a geometric point of view, doesn't seem to change at all. Pin stays a pin, roller stays a roller. But now I'm going to take this moment diagram, just lift it up, and set it on as what? As the loading. So there's my triangular shape. This is all positive, right? All positive moments. So what kind of load is positive? Up or down? Up. So we're looking at a loading scenario that looks something like this. We put some dimensions on here. So remember, this first part is 9 feet. Last part is 3 feet. And the intensity of that is going to be 11.25, and that's kip feet. And now we're going to divide it by E and I. And that's the problem we have to work. So we've transformed our original problem into a conjugate beam problem with the loading B equal to moment divided by EI. Now remember, let's go back and now recall that this problem wants to find the slope and displacement at the midpoint. So I'm just going to kind of come over here and pick the midpoint. So ultimately what I need at this midpoint, which would be 6 feet, is what? I want the shear and moment right there in the conjugate beam. That will map back to the slope and displacement in the real beam. So looking at this scenario, you want to work the left-hand side of that cut or the right-hand side? I think the choice is pretty obvious, right? So you want to go left. So if I want to go to the left side, what am I going to need? I'm going to need this shear force at A to get started, right? Now there would be a shear force over here at B, but I'm not going to need that along the way. So the first thing I need to do is find this shear force reaction at A. And probably the easiest way to do that would be the sum moments at B. You guys see that? All right, so let's do that first. So that means I need to resolve my distributed load up there into two forces. There's going to be one here. I'll call it F1. And I didn't give myself enough room here, so I'm going to kind of draw it here. F2. So F1 will be this triangular part of the load over the 9 feet with this height, 11.25. And then the F2 force will be this part, which is also a triangular load with the same height but a different base. So I'll just write these over here to the side. So F1 is going to be 1/2 the base, which is 9 feet, times the height, which is 11.25 kip feet, divided by EI. What's that going to be? That's probably going to be an odd number. Somebody's going to have to help me with that. While you're computing that one, I'll go ahead and calculate F2, which is going to be 1/2 the base, in this case, would be 3 feet. And again, the same height, 11.25 kip feet divided by EI. So what's the first value here? Anybody get that? 50.65. 50.625, and that's going to be kip feet squared over EI. And I guess this other one is a third of that, right? Like 16 something? 16.875. Try to squeeze it in there. And those are going to have units of kip feet squared over EI. All right, so I'm trying to find the shear at A. So I'm going to sum moments at B. Make sure it's at equilibrium. So summing moments at B, both F1 and F2 create what kind of moment about B? I'm using right-hand rule for positive, and they're opposite that, so they're both going to be negative. So it'll be F1, which is 50.625 kip feet squared over EI. I left off my minus, sorry. That's the force, and what's the distance? So what's the distance from B to the centroid for F1? Well, I go 3 feet just to get there, and then how far from this big end, the high part of the triangle, to the centroid? A third the distance, right? A third of 9 is 3, so 3 plus 3 should be 6. And then F2, which is a value of 16.875, and that's kip feet squared over EI. That's the force. And what's the distance from B to that centroid? Well, it's 2/3 the distance, and the distance is 3. 2/3 of 3? 2. And then all the way over here, I've got my reaction at A. It's also negative, and its distance is the total, which is 12. So what is the shear at A? It looks like it's going to be negative. I'll let you guys figure that out.
34.5.
34.5? Anybody else get 34.5? No? No. Anybody? Bueller? What? 34.5?
28.125.
28, that's different numbers. This should give you about 25 something.
28.
This should give you something like another 2. I think 28 sounds better. What is the answer?
28.125.
Anybody else get that? Yeah, now the heads are bobbing. Okay, great. 28.125, and that will be kip feet squared divided by EI. Okay, so now that I've got that result, I can go back and make a cut. So I'm going to come over here and draw that free body diagram. So it's going to be, this is going to be about the center. I just solved for this. I assumed it was up. I got a negative sign, so actually it's down. So that's going to be my 28.125 kip feet squared divided by EI. We're cutting in at the center, so that's 6 feet. At the cut, I'm going to be interested in the shear and the moment. So there's the positive values for those. So now what I have to do is figure out what's the intensity of the load at 6 feet. Well, I know as I go from 0 to 9 feet, I go up to 11.25. This is 6 feet, so that's 2/3 of 9. So what's 2/3 of this? 11.25. 7.5. So this intensity will be 7.5 kip feet divided by EI. That sound okay? So I'm going to resolve that into a concentrated force, which I'll call F3. And F3 is a triangle. So that'll be 1/2 the base, which is 6 feet, there's the base, times the height, which is 7.5 kip feet divided by EI. And that looks to be 22.5. Okay, so the height of the loading is 11.25, right? So this height is to 9 feet, as this is to 6 feet, right? It's linear. It's basically the slope. The slope of this line is constant, right? And what's the slope of the line? Rise over run. So this number, 11.25 to 9, that is constant for any point on this curve. So if I want to go 6 feet over, then I can figure out what this is by the slope. So all I did was say, 6 is 2/3 of 9. So this should be 2/3 of 11.25. I think this is 22.5. You guys get 22.5? So 22.5, and that will be kip feet squared over EI. So now I'm ready to go. I got all my pieces. So let's start first with the moment. So I'm going to sum moments about the cut that I just made. Looking at this free body diagram, there's my internal moment. I'm assuming right-hand rule, so that moment is positive. What's the moment created about the cut surface for F3? Positive or negative? Negative. So it's going to have a force of 22.5 kip feet squared over EI. That's the force. What's the distance from the cut to the centroid of this triangle? Which should be 1/3, and 1/3 of 6 is 2. The other thing you need to take care of is the reaction force. What kind of moment is it create about? Positive or negative? Positive. So that's 28.125 kip feet squared over EI. And that distance is the total, which is 6 feet. I think that's it. This number looks way bigger than that, so it looks like the moment is going to be negative, and I'll let you guys figure that out for me. I'm going to guess it's 128. I have no idea. 123? 0.75. 123.75. And that's going to be kip feet cubed over EI. Now we can stop right now and at least try to determine if a minus sign is appropriate here. How do you expect this beam to bend or deflect? It's probably going to look something like that. And that kind of deflection is negative or positive on our sign? It's negative. So at least we got that part right. That's comforting. To get the actual numerical value, I'm going to have to divide by EI. But I'm going to hold on to that for a second. Let's get the slope. Well, to get the slope, I'm going to find the shear. And to find the shear, I'm going to sum forces in the y direction. So looking at my free body diagram, my shear is acting down. I'm assuming up is positive, so that's a negative shear. My force 3 is up, that's positive. Force 3 was 22.5 kip feet squared divided by EI. And then what else? Oh, over here, my reaction force is down. That's negative. That's 28.125 kip feet squared divided by EI. So it looks like the shear is going to be -2, right? It's going to be really small, isn't it? What is that exactly? -5 exactly? 5.625. 5.625. We've been carrying that around for a while. Well, we might as well just keep it up. Kind of running out of space here and kind of jamming it in at the bottom. Sorry about that. So there's my shear force at the center, and then there's my bending moment. Now remember, moment maps to displacement, and shear maps to slope. Now this is a pretty small number. When you take 5 and you divide it by E and I you can see are quite large. Even with converting from cubic inches to cubic feet, this is going to be a really, really, really small number. Plus, it's negative. And that kind of makes sense. That means that at the midpoint here, the beam is still slightly pointing down. So at some point, the slope will go to 0, and that'll be the maximum value, and then it'll start going up and become positive. We haven't reached that point. So it's kind of telling you that the displacement at the midpoint is still just a little bit to the left of the actual maximum displacement. I've run out of paper here to finish this off, but all you have to do is divide by EI, convert cubic feet to cubic inches, do the same thing here, convert square feet to square inches, and you get the numerical value. So any other questions about that?